Good morning everyone, especially to our professor, Sir Manny Ryota, and to my classmates. I am Jenelene Yanag and my topic is the atmosphere, focusing on the subtopic structure, ions, and greenhouse gases. So what is an atmosphere? An atmosphere is a gaseous layer surrounding the Earth. In other words, our Earth is surrounded by a thin layer of gases. It is thin when compared to the size of the Earth. Yet, this thin layer has its own influences on various processes that takes place on Earth. It contains a mixture of gases with some impurities. So what's in the Earth's atmosphere? So it is a mixture of transparent, odorless gases and aerosols held to Earth by gravity. There are three main types of constituents. The permanent gases. Examples are the nitrogen, oxygen, and argon. We have also the variable gases, composes the greenhouse gases and reactive gas species. Examples are the carbon dioxide, methane, and water vapor. And the last one are the aerosols, the non-gaseous components of atmosphere. Examples are the sea salt, soot particles, and volcanic ashes. The permanent gases are mostly passive in weather-related processes. The nitrogen, oxygen, and argon constitute 99.9% of the atmosphere. The variable gases and aerosols occur as a result of both natural processes, example is the carbon cycle, and the human activities, example is the burning of coal. And it also affects transmission of radiation through the atmosphere. The table shows the different gases in the atmosphere, its percent by volume, parts per million or the ppm, and its symbol with its importance. So we have the nitrogen, oxygen, argon, and carbon dioxide. We have also other present gases and aerosols of the lower atmosphere. In the table, the following are the neon, helium, methane, krypton, nitrous oxide, hydrogen, xenon, and ozone. Earth's atmosphere has a unique composition of gases when compared to that of the other planets in the solar system. And as you can see in the pie chart, the nitrogen composes mostly of the Earth's atmosphere. One of the variable components in the atmosphere is the water vapor. The amount of water vapor in the air varies considerably, from practically none at all up to about 4% by volume. Now the question is, why is such a small fraction of the atmosphere significant? Water vapor is the source of all clouds and precipitation. However, the water vapor has other roles. When water changes from one state to another, it absorbs or releases heat. This energy is termed latent heat, which means hidden heat. Water vapor in the atmosphere transports this latent heat one region to another, and it is the energy source that helps drive many storms. Another variable component are the aerosols. The movements of the atmosphere are sufficient to keep a large quantity of solid and liquid particles suspended within it. Although visible dust sometimes clouds the sky, these relatively large particles are too heavy to stay in the air for very long. Still, many particles are microscopic and remain suspended for considerable periods of time. They originate from many sources, both natural and human-made, and include sea salts from breaking waves, fine soil blown into the air, smoke and soot from fires, pollen and microorganisms lifted by the wind, ash, and dust from volcanic eruptions, and more. Collectively, these tiny solid and liquid particles are called aerosols. There are also meteorological standpoints. First is, many act as surfaces on which water vapor can condense, an important function in the formation of clouds and fog. Another one is that aerosols can absorb or reflect incoming solar radiation. Thus, when an air pollution episode is occurring or when ash fills the sky following a volcanic eruption, the amount of sunlight reaching Earth's surface can be measurably reduced. Finally, Aerosols contribute to an optical phenomenon we have all observed: the varied use of red and orange at sunrise and sunset. Another variable component, the ozone. It is a form of oxygen that combines three oxygen atoms in each molecule. There is very little of this gas in the atmosphere, and its distribution is not uniform. In the lowest portion of the atmosphere, ozone represents less than 1 part in 100 million. It is concentrated well above the surface in a layer called the stratosphere. Then what is pressure changes? Atmospheric pressure is simply the weight of the air above. At sea level, the average pressure is slightly more than 1,000 millibars. This corresponds to a weight of slightly more than 1 kilogram per square centimeter or 14.7 pounds per square inch. The pressure at higher altitudes is less. One half of the atmosphere lies below an altitude of 5.6 kilometers or 3.5 miles. At about 16 kilometers or 10 miles, 90% of the atmosphere has been traversed. And above 100 kilometers or 62 miles, only 0.0003% of all gases making up the atmosphere remains. Even so, traces of our atmosphere extend far beyond this altitude, gradually merging with the emptiness of space. So what is temperature changes? The upper atmosphere was partly known from indirect methods. Data from balloons and kites had revealed that the air temperature dropped with increasing height above Earth's surface. The graph shows the structure of the atmosphere based on temperature differences. Note that the pauses are actually not lines but are broad regions that merge. The Earth's atmosphere is made up of 5 different layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Why is the atmosphere divided into 5 different layers? It is because the atmosphere is not uniform. Its properties change with altitude. And there are 2 properties changes with altitude: the air pressure and the air temperature. The first layer is the troposphere. The troposphere is the layer of the atmosphere nearest to the Earth. The troposphere goes from 0 kilometer to 16 kilometer. All weather happens in the troposphere. More than half the air in the total atmosphere is in this layer. The temperature drops as the altitude increases. Harmful ozone is found here. It creates smog. By the way, what is an ozone and what is a smog? An ozone is a gaseous layer in the upper atmosphere that protects the Earth from harmful ultraviolet radiation. At lower levels, ozone becomes a major pollutant. And what is smog? A smog is a pollution formed by the interaction of pollutants and sunlight, or the photochemical smog, usually restricting visibility and occasionally hazardous to health. The second layer is the stratosphere. The stratosphere goes from 16 km to 50 km. Its temperature goes up with altitude. And then most jets fly in this layer. The protective ozone is at the top of the atmosphere, and it protects us from the ultraviolet radiation of the sun. Rivers of air called jet streams can be found at the base of this layer. The third layer is the mesosphere. It goes from 50 km to 90 km. And in the mesosphere, the temperature drops with altitude. It is the coldest layer of the atmosphere, and the meteors burn up in this layer. And also the radio waves are reflected back to Earth in this mesosphere. And now the fourth layer is the thermosphere. This layer goes from 90 km to 300 km. And in this thermosphere, the temperature goes up with altitude. It is the hottest layer of the atmosphere. Curtains of light called auroras occur in this layer. And the ionosphere is found in the thermosphere also. This is the component of the thermosphere that makes the auroras. And the last layer, the exosphere. It is the outermost layer of the atmosphere, and its temperature goes up with altitude. The satellites orbit Earth in the exosphere. Why is the atmosphere very important? First is it sustains life on Earth. It contains life-supporting oxygen in sufficiently large quantities. Constant concentration of oxygen is maintained through oxygen cycle, along with other biogeochemical cycles. These cycles connect the atmosphere with hydrosphere, lithosphere, and biosphere. It is said that the atmosphere does not function by itself, but it functions in conformity with other spheres on Earth. Second reason is that the atmosphere is the transparent layer through which life-sustaining solar radiation passes and reaches the Earth's surface or into the water. It is a wonder why solar radiation is mentioned as a life-sustaining one. It is mentioned so because solar radiation is the only source to supply energy for photosynthesis to take place on Earth, which thereby supports all other life. And the last reason is that heated Earth emits the energy in the form of infrared radiation during nighttime, and this radiation is absorbed by carbon dioxide, water, and few other gases. This process results in greenhouse effect. Thus, the atmosphere is kept warm during night. It will become so cool and intolerable for living organisms. Consequently, understanding the atmosphere and its functions and behavior is quite complex. However, with available knowledge, scientists try to comprehend to the extent possible. Thus, understanding of the atmosphere has become very essential and important. All the above processes make the atmosphere a dynamic atmosphere. Let's have the greenhouse gases. The naturally occurring greenhouse gases include carbon dioxide, or the CO2, methane, CH4, nitrous oxide, N2O, ozone, O3, and the water vapor, H2O. The greenhouse gases plays an important role in regulating atmosphere's energy budget by absorbing some of outgoing terrestrial radiation. Increases global mean surface temperature. In the process, the natural greenhouse effect. Atmospheric concentrations of almost all these gases have increased since 1800s due to first, combustion of fossil fuels, second, deforestation and agricultural change, the livestock and food production increases. Anthropogenic greenhouse gases include chlorofluorocarbons, methyl bromide or the pesticides, the solvents, and the halons. These were released into atmosphere since 1930s, and the consequence, enhanced greenhouse effect. The table shows the changes in atmospheric concentrations of greenhouse gases. We have the gases carbon dioxide, methane, nitrous oxide, chlorofluorocarbon 11, and CFC12. We have also here its concentration from 1750 to 2011 with the units of ppmv, parts per million by volume, and ppbv, parts per billion by volume. Example, the carbon dioxide. Its ppmv in 750 is 278 and it increases to 390.4 ppmv in 2011, as well as the CFC11 from 0 ppbv to 0.24 ppbv in 2011. The carbon dioxide or the CO2. It is the most important greenhouse gas after water vapor, which is involved in complex carbon cycle. Its natural sources are respiration, decomposition of organic matter, forest fires, volcanic eruptions, evaporation from oceans. Its anthropogenic sources are fossil fuel combustion, deforestation and biomass burning, and manufacture of cement. And sinks, or the removal from atmosphere, plant photosynthesis and absorption by oceans. Methane, or CH4. Its primary natural source is the natural anaerobic. Example is the oxygen deficient processes in wetlands and rice paddy fields. Other natural sources are animal digestive processes. Cows can produce up to 200 liters a day. The termites and the forest fires. Its anthropogenic sources are fossil fuel combustion, biomass burning, and disposal of refuse in landfill sites. And its sinks oxidize to CO2 and H2O, or carbon dioxide and water, by complex photochemical reactions in troposphere. Nitrous oxide, or N2O. Its primary natural source is microbial activity or nitrification in soils and oceans. Its anthropogenic sources are fossil fuel combustion, biomass burning, and nylon nitric acid and nitrogen fertilizer production. It sinks, oxidized to nitrogen oxides by photochemical reactions in stratosphere. The CFCs, or the chlorofluorocarbons. We have two types, the chlorofluorocarbons 11 and 12. Anthropogenic uses includes used as coolants in refrigeration, propellants in aerosols, and expanders in foam products. Its concentrations: distinct increase in concentrations between 1960 to 1990. And its impacts: Montreal Protocol led to a huge decline. Then we have also the tropospheric ozone, or the O3. It is produced by a series of complex chemical reactions, including pollutants from car exhausts, or the nitrous oxide and hydrocarbons reacting with sunlight. More vehicles means greater concentration, thus increasing the greenhouse effect. It can damage human health and vegetation, and the key ingredient of urban smog. The question is, what if Earth did not have greenhouse gases? The table presented is an example of why we want to have greenhouse gases. They make our planet inhabitable and bring the temperature up to a level humans can live in. It does not mean that the temperature everywhere on every day is equal to 59 degrees, but just that there is a dramatic change because of the GHG. We know this because we can look at other planets, Mars and Venus usually, and compare their temperature and atmospheres to ours. So what is a greenhouse effect? An example is that when we get into a car on a hot day, it feels much warmer inside the car, and that is because of the trapped air. The illustration shows the greenhouse effect. Some sunlight that hits the earth is reflected and some becomes heat. That CO2, or the carbon dioxide and other gases in the atmosphere, trapped heat, keeping the earth warm. This is a picture of the numbers that give us the greenhouse effect. Most of the solar irradiation reaching the lower atmosphere is visible light, but there are other wavelengths present as well. Some of the gases, including the water vapor in the atmosphere, reflect incoming solar irradiation. Some allow it to pass through to the Earth's surface, where it is absorbed, and some absorb it. The radiation, mostly visible light, that is absorbed in the atmosphere or by the Earth's surface, is re-emitted as long-wave infrared energy or heat. When long-wave radiation interacts with the atmosphere, different molecules will reflect, absorb, or allow it to pass through to space. The passing of long-wave radiation from the Earth's surface to the atmosphere back to the Earth's surface and so on is the fate of large quantities of solar irradiation and a major positive forcing. So the atmospheric gases that allow visible light to pass through but then absorb and re-emit long-wave radiation are of huge interest to us. They can be thought of as like the car's windshield. We call this greenhouse gases because they create a greenhouse effect in the Earth's atmosphere. Heating the atmosphere, the greenhouse effect. Approximately 50% of the solar energy that strikes the top of the atmosphere reaches Earth's surface and is absorbed. Most of this energy is then re-radiated skyward. Because Earth has a much lower surface temperature than the Sun, the radiation that it emits has longer wavelengths than solar radiation. The atmosphere as a whole is an efficient absorber of the longer wavelengths emitted by Earth or the terrestrial radiation. Water vapor and carbon dioxide are the principal absorbing gases. Water vapor absorbs roughly 5 times more terrestrial radiation than do all other gases combined and accounts for the warm temperature found in the troposphere, where it is most highly concentrated. Because the atmosphere is quite transparent to shorter wavelength solar radiation and more readily absorbs longer wavelength terrestrial radiation, the atmosphere is heated from the ground up rather than vice versa. This explains the general drop in temperature with increasing altitude experienced in the troposphere. The farther from the radiator, the colder it becomes. When the gases in the atmosphere absorb terrestrial radiation, they warm, but they eventually radiate this energy away. Some travel skyward, where it may be reabsorbed by other gas molecules, a possibility less likely with increasing height because the concentration of water vapor decreases with altitude. The remainder travels earthward and is again absorbed by Earth. For this reason, Earth's surface is continually being supplied with heat from the atmosphere as well as from the Sun. Without these absorptive gases in our atmosphere, Earth would not be a suitable habitat for humans and numerous other life forms. That's all for my report. Thank you for watching and listening. God bless us all.